I'm working on a project that uses this ESP32 board together with this camera sensor and a built-in microphone. I plan to power it with a pretty beefy battery whose nominal voltage is about 20 volts, and as part of the project, I need a voltage regulator to step it down to 3.3 volts. So in this video, we'll walk through a step-by-step tutorial on how to design a custom buck converter that does exactly that. We'll cover everything from giving an overview description of what buck converters are, selecting the key components commonly used in these regulators, to laying out the PCB using advanced rules in Flux, while also discussing critical tips to help you avoid common design pitfalls. With that said, let's get started. A buck converter is a type of switching voltage regulator, and the primary function of any voltage regulator is to maintain a constant voltage supply even if you have fluctuating voltage inputs. Voltage regulators can be classified in two broad categories: linear regulators and switching regulators. Linear regulators are very simplistic and generate a stable output by dissipating excess power as heat. Switching regulators, on the other hand, are more efficient than linear regulators. However, this comes at a cost of a more complex design. With switching regulators, you can step up, you can step down, or even invert voltage. A step-up converter is usually referred to as a boost converter, while a step-down is referred to as a buck converter. And designing a buck converter is the topic of our discussion. So let's take a closer look at that. This is a buck converter. On the far left, you have your unregulated input voltage source, and then you have a switch that either turns on or turns off. When the switch is turned on, current flows through the circuit and charges the inductor. During this time, this diode will be off because it is reversed biased. And you can see that in these ideal diode voltage and inductor current waveforms. After some time, when the switch is turned off, the inductor releases its stored energy in the opposite direction, and this time the diode will be on. This diode is called a catch diode, and its purpose is to provide a path for the inductor current when the switch is opened. These waveform diagrams show how the inductor stores energy during the on time of the switch and releases energy during the off time, which is what enables the conversion from a higher input voltage to a lower output voltage in a buck converter. From this basic circuit, you can see we need a few things. We need a catch diode, an inductor, and an output capacitor. Let's now jump into Flux and see how we can build this thing. The first thing I want to do is go to my profile at Flux.ai and create a new project. I can create a new project using one of our manufacturer templates, and this will save me a ton of time when it comes to DFM later on. But for the sake of this video, I'll just start from a blank project. On the top left, you can see the name of the project. Flux gives a default random name, and you can change that by double-clicking on it to select everything and start typing a preferred name. I'll call this one buck converter, but feel free to rename yours to something equally descriptive. This is called the parts library. You can enter a keyword or a part number to search for a part. You can also use these filters. For example, this will allow you to only search for components that you've created, and this one will allow you to search in components that have footprints. You can even search across your preferred distributors. By default, you are searching the whole parts library. However, if I click this icon, check DigiKey, Mauser, and LCSC, for example, the results will only contain components which can be sourced from those distributors. I can also see the live pricing and stock information about that part even before using it. So when you get the part you are looking for, you just drag it onto the canvas. On the right side, you have the Chat and Inspect tabs. The Chat tab is where you easily start a conversation with Copilot and you can ask a bunch of questions. The Inspect tab is where you change the project description, properties, and you can also get live pricing information of your whole project. I'll change the project description to say something like, this is a voltage regulator. It steps down an input DC voltage of up to 40 volts to a stable output voltage of 3.3 volts with a maximum output current of 3 amps. There's a wide variety of buck converter ICs in the market, and so it's very important to know how to select the right IC for your application. Selection usually starts from your specific requirements. In our case, we already have these requirements. I can actually add those requirements to the project properties, and this is good for documentation and also to help the AI have context. Under the properties section, click Add, start typing max input voltage, select it, and click Add again. Similarly, we also want to specify the maximum output voltage. So click Add again, search for output voltage, select it, and click Add to add it. Finally, we want to add the output current. If it doesn't exist in the list of choices, just type out the whole property, then add the unit, and then click Add to add it. We know our maximum input voltage will be about 20 volts. We will want a regulated output voltage of 3.3 volts for our microcontroller at a maximum output current of 3 amps. For this project, we will use the LM2596 buck converter IC just because it's a very popular IC and it also checks all the boxes of our requirements. If you need to do more research because this is not the case for your application, you just need to do the same thing. Add the project properties the way we've done here, and then ask Copilot to recommend buck converters that meet those requirements, and then you can move on from there. For example, in this case, Copilot says that our choice is good and recommends other buck converters as well. If you click the recommended IC, you can immediately see if they exist in the parts library, as well as seeing their pricing and stock availability in real time. We are comfortable with the one we've chosen, so I'll just proceed with it. This IC has 5 pins plus a pad for additional thermal management. Normally, if it's a new IC, you'd start by looking at the reference schematic in the datasheet to see what each pin does and how it should be connected. You can also just ask Copilot for a summary of all that. For example, I can type, in a table format, describe the function of each pin of U1 and how they should be connected. Copilot will access the datasheet and retrieve all those information for you. And sometimes when the information is not directly stated in the datasheet, Copilot will use its knowledge to suggest solutions for whatever you ask. If I open the datasheet, and you do this by selecting the component, going to the Inspect tab if it's not currently open, and finding the datasheet URL under the Properties section and click it. If we look at the typical application circuit from this datasheet, you can see it has almost similar components that we've seen in the introductory section. We have a catch diode, an inductor, and an output filter capacitor. It also has a few more components like the input filter capacitor, a voltage divider network here, and another capacitor here. Whenever you're not sure what the function of a particular circuit or a section of a circuit is, you can just ask Copilot. Here I can take a screenshot of this section, go back to Flux, open the chart tab, I'll scroll to the bottom and continue the conversation by asking for an explanation of what each component in the schematic does. I had already taken a screenshot of the schematic and saved it on my machine, so to upload the image, I'll click this image icon, choose the image and click open. Copilot will analyze the image and create a nice table explaining everything to me. We will borrow a lot from the reference schematic in the datasheet and only change one thing to get our desired output. So I can begin adding all these passive components. We need an input capacitor C1 for filtering and preventing large voltage transients to ensure stable operation of the converter. And you can rotate components using the angle brackets key. In this video, I won't go very deep on how to use the equations given in the datasheet to find different values. If you want an in-depth tutorial, I'll suggest you check out this video by Phil's lab. He does an amazing job at explaining those concepts. We also need an output capacitor which smooths out any of the voltage ripple. For this application, it is recommended we use a 220 microfarad electrolytic capacitor. So we'll find that in the library, and this will do. and drag it onto the canvas. Next, we need to add the inductor. The datasheet recommends using a 32 microhenry inductor. So in the parts library, I'll search for 32 micro inductor and make sure the inductor I select can handle the output current, which in this case is 3 amps. So in our case, I'll choose this one. Next thing we need is the Schottky diode. Two important electrical characteristics to consider for this diode is the forward current reading and the reverse voltage reading. Make sure the diode can handle the maximum output current, which in this case is 3 amps, and has a reverse voltage rating higher than the input voltage, which in this case is 40 volts. The next thing I'll want to add is the voltage divider network. And this is where I'll change the values a bit. This circuit will give you a regulated 5 volts output. But remember, we want 3.3 volts as our output. We can change the output by changing the values of these resistors. And the change is governed by this equation. Assuming we let R1 be 1.21K and we solve for R2, we get that our R2 is about 1.28K. This is fine, and we can probably find it from one of the distributors, but I'll prefer to use a standard value just because it's easier to source standard value resistors. The closest standard value to this is 1.27K, and this will also be sufficient for our use case. For this example, I'll use generic resistors. Generic components are great when you want to change the package size on the fly. I'll go back to the Inspect tab, click here, and select the package you want to use. Here I'll choose the 0805 and also change the value to what we have calculated. To duplicate it, I just copy and paste by pressing Ctrl+C and Ctrl+V. And then finally, I'll also change the value of this resistor. I also need a capacitor for the feedback stability and noise reduction. For this capacitor, we can use a ceramic capacitor, and the recommended value is about 5 nanofarad. At this stage, I can begin wiring up my schematic, but I need 2 terminal blocks where I will connect the physical input and output wires. So I'll search for a 2-position terminal block and add it to my schematic. Since I want 2 of this, I'll duplicate this one, and I can flip components using the F shortcut key. To connect components using the wire, I go to one of the pins until the white little dot appears and click it to start the wire. I move my mouse to the other components I want to connect to and do the same thing. You can also select a bunch of components and drag them around without losing the wire connectivity, so you can do this to arrange your schematic. The inductor is connected to the output pin, so I'll connect that and also the diode and output filter capacitor. I'm referencing the application circuit in the datasheet, but you could ask Copilot exactly what to do and it will tell you. To add the ground net, I will go back to the parts library, and it should be among the top parts, so just drag and drop it to your canvas. I will then connect it to the negative side of the terminal block. I'll copy and paste it to the inductor and the output filter capacitor and connect those two. I'll then use a power net portal to indicate that this is a power net. I'll then change the name of this net portal to 12 volts or even 20 volts. After that, I'll take some time to connect the rest of the components in the same way. Here I also use the power net portal to indicate this will be the 3.3 volts rail. We will reuse this project as a module in later videos of this ESP32 design series, and converting a Flux project into a module for reusability is very easy. I will not cover that in this video. If you want a deeper dive into sublayouts and modules in Flux, I've linked a video in the description box below, so feel free to check that out. I'll drag and drop the terminal object into my schematic and connect it to the on-off pin of the buck converter, which will allow us to control it when we have a microcontroller later on. After that, I'm now ready to begin layout and routing. I'll change to the PCB tab and begin setting up my board. It's important to set up your design rules to ensure your board is manufacturable. Different manufacturers have different capabilities, meaning you will have to either contact them directly or double check from the manufacturer's website to ensure you comply with the design for manufacturing guidelines. Another option you have in Flux is to start a new project using one of the manufacturer templates, which comes with all the design constraints so that you don't have to manually input them in the tool. Since we started from scratch, we'll have to manually add those design constraints into Flux. I want to start by setting up my trace widths and via configurations. I know they have to be thick enough to handle about 3 amps, so to begin, I'll ask Copilot to recommend appropriate trace widths for the different power rails in this project. At the same time, I'll ask for via configurations considering I will want to use JLCPCB services to manufacture this board. Copilot will take a minute and then give me all those values in a nice table format, and then I can decide to either use those or other values I deem appropriate. For this project, you can use a 2-layer board, and that will be enough. However, for the sake of this example, I'll use the default 4-layer stackup so that I can show you how to handle ground planes in Flux. Next, I want to assign different trace widths for my different power rails to ensure proper current handling. I'll first start by renaming my nets of interest. I can see this net connects the 3.3 volts power portal, so I'll rename it to 3.3 volts. This net connects the 12 volts power portal, and so I'll rename it to 12 volts. And that's how you rename nets in Flux. Next, I'll select the 3.3 volts rail under the nets object, and on the right, I'll add an object-specific rule by clicking Add, searching for trace width, and clicking Add again. After that, I can change the value to 80 mil. I'll do the same for the 12 volts rail. Select it, click Add, search for trace width, and click Add again. After that, I'll also change the value to 80 mil. For the rest of the nets, I'll use advanced selector-based layout rules to control the trace width and override the default rules. I will show you how to add preferred trace width to your nets and also hide designator values. Let's start with preferred trace widths. I want to tell Flux that I'd prefer certain kinds of sizes for the rest of the nets in the design. You do this by first going to the Rules tab, clicking Add Rule Set, select the newly added rule set. On the right, you can change the name of the rule set. I'll call this one Preferred Trace Width. You can add a brief description of what the rule does here. And then in the selection criteria, I want to select all the nets in the design. So I'll just type net. Click Add Layout Rule, search for Preferred Trace Width, and click Add again. After it's added, you can type the preferred trace width. In my case, I'll add 10, 20, 40, 60, and 80 mils, and make sure there are spaces in between them. If you want this rule to take precedence over other rules, you need to add the important tag at the end. Sometimes you want to hide designators or values for specific components to keep your layout clean and readable. To hide designator values, we'll apply a similar selector-based layout rule in a similar way. Click Add Rule Set, select the newly added rule set, rename the rule set to Hide Designator Value. In the selection criteria, I'll target components with value in their name. So I'll type this syntax into the selection box. If you want more information on the syntax used in these selector-based layout rules, I've linked supporting material in the description box below, so feel free to check that out. Under Layout Rules, I'll click Add, then search for Enable and click Add again. For this rule, I'll change it from True to False because I want to disable the visibility, and then add the important tag for it to override the default rule. In an example where the designator is not hidden, you can do this manually. You double-click on it and make sure the selection box is only around it, indicating that it is the currently selected object. Go back to the objects list, find the selected object, then click these 3 little dots to bring up the context menu. And then you want to choose Disable to hide it. With our project all set up, we can begin laying out our PCB. This means placing components to where it will be easier to route them. I'll start with the IC since it's kind of my centerpiece and just place it centrally as a starting point. Then I want to make sure the input capacitor is as close as it can physically be to the IC. This is just to reduce and filter the input noise. Then I also want to place the input terminal block somewhere close to the input capacitor for cleaner routing of the trace. I'm actually not sure which is the front side of this terminal block, and so I can switch to the 3D to confirm that. So it appears I need to rotate this connector. Next, the voltage divider network is not super critical, but I want to place them somewhere near the feedback pin. I'll start with the capacitor across R1 and then move to R1. I can double click on the designator to select it and move it out of the way for a cleaner PCB. It's also important to use the air wire and alignment guides to make sure your components are nicely aligned. I'll drag R2, rotate it, and make sure it is in place, and then move the designator beside it. I want to then move to the Schottky diode. I'll make sure it is close enough to both the output pin and the inductor. So I'll also move the inductor close to the diode, and this will ensure that I minimize the switching losses and noise. Next, I'll place the output capacitor and the output terminal block close together. Finally, I can make the layout a bit tighter by moving some of the components closer together and ensuring the designator values are properly arranged. We can then resize our board by selecting the layout object and then changing the values to whatever we want. I think this board can be about 40 by 37 millimeters. Important note is to always check the 3D view to look for anything that might not look right and make sure to adjust that. Before I begin to route out my board, I want to show you how the ground planes in Flux work. A layout object by default comes with the ground plane on all layers, and you can see this when you turn on the different layers of the PCB. All the layers are connected by stitching vias, which you can see when all the layers are turned off. If you want to change the layers that have ground planes, you select this ground net, go to Object Specific Rules and click Add, search for Connected Layers rule and click Add to add it. Here I can choose whichever layer I want to have the ground plane. For example, I can choose only the top and bottom layers and they will adjust in real time. Since I don't have any signal traces running in other layers, I'll just leave all layers with the ground plane. These ground planes are connected by many auto-generated vias which are called stitching vias. In my case, I want to increase the number of these vias so that I can improve the overall grounding performance of my board. I do this by making sure the ground net is still selected, and under Object-Specific Rules, I want to click Edit, then Add. I'll start searching for stitching and then choose this option. Once it's added, I'll change the spacing to 2 millimeters by 2 millimeters, which I think is good enough for this design. To start routing, I click on this white little dot called a routing touch point and move my mouse to the other end where I want to finish the trace. I'll do the same thing here. I can see this trace is too big to connect to the pad, so I can press the shortcut key W to change the trace width and neck into the pad with a smaller trace. I'll proceed to connect the Schottky diode and then the inductor with a wide enough trace. I'll follow that up with the feedback line and then the output capacitor and the output terminal block. Once done, you can open this DRC tab to check for any problems like overlapping copper or trace or any unfulfilled air wire. Since we don't have any of those errors, we are good to continue. The final thing here will be to export our manufacturing files and send them to our preferred manufacturer. You do that by clicking the Flux logo at the top left, go to Export, then choose Gerber. I'll repeat this for the bill of materials and the pick and place files, after which you're ready to upload those files to your preferred manufacturer's website. I followed these steps and designed this dynamic power management board which accepts input from various power sources like solar, USB, and battery. If you want to check it out, I've linked it in the description box below. If you want to see how I designed that board, or if you have any questions regarding the materials we've covered in this video, please leave a comment in the comment section below. If you found this tutorial useful, make sure to hit the like button and subscribe to the channel. Thanks for watching, and I'll see you in the next one.